Okay, step 7 is basically you put everything together. That's what step 7 is. Complete the root locus graph including the departure from complex pole or arrival at complex 0. So basically I would say there are 6 steps. I call it a step 7, that's okay. So let's look at an example. I think this is either example 7.4 in the book or exercise 7.4, I forgot. So we have 1 plus k over s4 plus 12s cubed plus 64s squared plus 128s. That is the denominator of ds. Okay, the first thing is we are going to figure out this on the next page. So first go to the next page. First actually just look at that. So from this we know that there is no zero, finite zero, that is there will be infinite zeros. There are no finite zero. There are poles at s is equal to 0, s is equal to -4, and s is equal to -4 plus minus j4. So there are 4 poles. Remember, that means there will be 4 zeros sitting at infinity. So we put down those x's. S is equal to 0, s is equal to -4, -4 plus j4, and -4 minus j4. That's our first step. Second step is to figure out what will be the part of real axis that will be part of the root locus. So if we look at the right side, we have a single pole. That means odd number. That means this whole x-axis is part of the root locus. If we stand on the left of this pole, -4, and look towards our right, we have 1 and 2. That's an even number. That means this is not part of the root locus. That means anything beyond -4 on the negative x-axis is not part of the root locus. So we're going to make a line here that this is part of the root locus. Step number 3. What is step number 3? We're going to find the asymptotes along which the zeros at infinity will be located, and the point that and where the asymptotes are going to intersect on the x-axis, that is the centroid. So to find the centroid, this is the centroid. To find the centroid, right here we have sum of all the poles minus sum of all the zeros divided by n, where n is the difference between poles and zeros, which is 4, of course, because there is no zero. All the zeros are sitting at infinity. So we sum all the poles, -4, -4, -4, 12, because when you sum these poles, negative j4 and positive j4 will be cancelled out anyways. So you have -4, -4, -4, -12. So -12 over 4, -3. So your centroid is at -3 right over here. Okay, what will be the angle of asymptotes along which the zeros will be located? We're going to go ahead and figure this out using this 2k plus 1 over n minus m, and since we have 4 zeros, we're going to take k is equal to 0, 1, 2, 3, and when we put that, we're going to get these angles: 45, 135, 225, which is -135, and 315, which is -45. So we're going to make those angles 45 degrees, 135 degrees, -135 degrees, and -45 degrees. So along this, that means 1 0 is sitting right over there along this line, 1 0 is sitting right over there along this line, 1 0 is sitting right over there along that line, and 1 0 is sitting along this line over here. So we know exactly how the curve is going to turn. We know that because it's going to turn along the asymptotes. Alright, so next step, find the breakaway point, because we have all the real roots over here on the x-axis, and eventually when you keep increasing k, they're going to break away from the real axis and go in the x and y plane, or imaginary plane, becomes complex root. So to find the breakaway point, number 4, before that we're going to find the breakaway point is number 5. Step number 4 is to find where it crosses the imaginary axis, that is where is what point it's going to become critically damped system. So we're going to create the polynomial equation. This is our polynomial equation right here. So it's going to be s times s plus 4 times these two roots here plus k equals 0. That's going to be our polynomial. which will turn out to be s4 plus 12s cubed plus 64s squared plus 128s plus k, and we're gonna put it in the Ruth Howard's array and calculate this. You know how to calculate all this. This B3 is 53.33, this is K, C3 is this. Let's see, C3 equation is right here. This is C3 equation, and we know that when C3 is equal to 0, that means it will be critically stable system, and then we can find the value of K from the S square equation. So first we're going to find out when C3 is going to become 0 from this. When C3 is 0, the value of K is 568.853, because this is C3 right here. So we're going to go ahead and put this equation over here, 53.33 S square plus 568.853, 53.33 S square plus this, and from that we will know that value of S is positive negative J3.266, so it will cross at positive negative J3.866. So it is going actually kind of on top of this asymptote, and then it's going to become along the asymptotical line. How do I know it's going on top of the asymptote? Because we can always find where this line is going to intersect the y-axis. We know this is what, 3. So when we have this line intersecting the y-axis, we know the angle, we can calculate the angle over here, and we can determine at what value it is going to be intersecting the y-axis. This angle is 45, so we can determine sine of 45 is opposite side over x-axis. So if you want to know the opposite side, what is the height of the opposite side, then sine of 45 times the x-axis, that's going to give us the y-axis. So we will figure out what is this value where asymptote will cut the y-axis, and it is cutting, looks like it is cutting at J3 and negative J3. So this 3.48, whatever the value we got, is going to be on top of that, but then again it's going to go on top, but then it's going to go and become parallel, and it's going to move along that asymptote along which the 0 is sitting. The next point is the breakaway point. We'll have to find where the x-axis, if we keep increasing value of K, where does it leave the x-axis, what point it leaves the x-axis, and then start moving along the asymptotes. So to find that breakaway point, we know we have to take the derivative of dk over ds, and when we take the derivative of dk over ds, the breakaway point, which is the real value on the negative axis. Observe that we have 3 roots, but 2 are complex conjugate. So of course these roots are not going to be present on the real axis, so only the one that presents on the real axis is going to be one that you will be considering. So negative 1.5767, that is the breakaway point right here. So we know it's going to leave the x-axis from here. It's going to go in this direction, and then it's going to go in this direction. And the last one, we have to do it in this one because we have complex conjugate poles. So we need to know what is the angle of departure. So the angle of departure, let's see if it's on this page. No, it's on the same page. The angle of departure right here, I take a point very close to this point, negative 4 plus J4, and I'm calling it my S1, and the angle from S1 to the point is theta 1. So I'm trying to figure out what theta 1 is. So I'm going to take I'm going to create a vector from other poles to this point. So when I create the vector from this pole to the point, that's going to be 90 degrees. So that's one of the 90 degrees. Okay, when I make the when I make it from this point over here, that's another 90 degrees right here, a straight line. So that's another 90 degrees. When I make from this, I make a vector right here And how I'm going to calculate the angle? This angle right here. So again, I know that this is -4, this line, and this line is also 4. So this is 4 and this is 4. That means this angle is going to be 45 degrees, right? X and Y are same. So if you calculate, you can calculate sine basically, right? Or not sine, sorry, since we don't know this, I mean, we can figure out what is the hypotenuse of 4. That's base square plus the opposite side square, perpendicular square. So we can figure out what is the length of this hypotenuse since it's a right angle triangle. But if you want to take tangent, the tangent is opposite side over adjacent side. And from that, since both the sides have equal length, the angle this will be 45 degrees. Hence, this angle will be 180 minus 45 will be 135 degrees from this pole at s is equal to 0 to this pole. We are going to this pole because the point is located very close to this pole, which is -4 plus j4. So that's 135 degrees. And the sum of all the angles equals 180. So theta 1 is going to be -135 degrees. That means the angle of departure from this is going to be 135 degrees along this line right here. So it's going to depart, the curve is going to depart from here, and then it's going to go along this asymptote. It's going to curve. Again, it's, you know, it's not 100%, but this is how it's going to curve. Not all the values have to be exact when you're drawing with your hand. Of course, if you draw with a computer, all the values will be exact. So it's going to go at -35, it's going to depart at -135, and then go curve and go along this line because the 0 is sitting along 135 degrees. The same will be true for the complex conjugate, except it is going to go in the opposite direction. It's going to leave at 135 degrees instead of -135, and then go along -135 degrees along this asymptote. So this will be the root locus for this. We can when we discuss project number 2, then we can draw the root locus and see how close it's gonna be with this.